One of the worst things about becoming a physicist after growing up on science fiction was finding out that traveling faster than light speed is impossible, and not from lack of imagination or by casual hyperbole, just not allowed under known physics and at best not technically banned in certain theoretical math. To make it worse though is when you find out that even going close to light speed is very nearly impossible. So it's not just that getting to some place like Alpha Centauri, our nearest neighboring star, might take 4 years instead of 4 days, or even 4 hours like it might in sci-fi, but that getting there even in 40 years requires optimistic outcomes for technologies we don't have yet, like fusion. Chemical rockets combined with gravitational assist can offer us almost 0.1% of light speed, making a journey in 4,000 years instead of 4. And we have some options for ion drive or nuclear propulsion that could push that to 1%, maybe even a few percent for something like the Orion drive that drives itself along by blowing nuclear bombs out behind it. Fusion might get you to 10% or even a bit higher, but nowhere near 50%. Last month I did an impromptu episode on Buster-Ramscoop spaceship drives, and it got me thinking we should discuss what options actually let you get close to light speed. At least better than 80%, and some that can potentially get to 99% or better, so I thought we would cover them briefly in today's Nebula exclusive. Now, for the sake of brevity, we won't repeat all the reasons why getting close to or exceeding light speed doesn't work. We've covered that elsewhere, but the short form is that it isn't really the mass of your spaceship that you have to push to accelerate. It's the total energy of your spaceship that you have to push to speed. We have a lot of different types of energy in and around us, and sitting still, you basically just have your mass energy and your thermal energy, and the one is vastly bigger than the other, so we don't bother factoring into calculations. We just use mass because unless you're going incredibly fast or are incredibly hot, then your mass is basically the same as your total energy. As you get faster though, you gain energy of motion or kinetic energy, and this adds to your total energy, which means you now have to shove even harder for every extra bit of speed. You are gaining bits of speed and have to push them too. Your mass energy is that E equals mc squared we're all familiar with, where m is mass and c is light speed. So essentially as you get near to light speed, your kinetic energy is beginning to rival your mass energy, and you have to push both now. Loosely speaking, ultra-relativistic speeds are those at which your kinetic energy now exceeds your mass energy, and that happens at 86.6% of light speed, and we will classify anything beyond this speed as ultra-relativistic for today. Now that ratio can go much higher, and we have created particles with millions of times more kinetic energy than mass energy, and indeed the current record is actually a naturally occurring one, the oh my god particle detected back in 1991 that was calculated to be moving at 99.999999999999999999999999999999999999999% of light speed, assuming I didn't miss any nines in there. So to be clear, we're not talking science fiction today. Yet, anyway. We have made things travel at ultra-relativistic speeds, and nature has too. But you can't get to light speed because even when you have a particle whose total energy is 99.999999999% kinetic and less than a billionth of its total energy is mass energy, that's not zero. If you've got mass, you can't get to light speed, just ridiculously close to it. As an upside, it is your ratio of mass to your combined energy that dictates how you experience time. Photons and other particles actually move at light speed and have no rest mass and experience no time. And if you have an equal kinetic energy to mass energy, such as 86.6% of light speed, you experience half-time compared to something stationary. If your kinetic energy is 9 times your mass energy, only a tenth of your energy is mass and you experience time at a tenth the normal rate, which would be at 99.5% of light speed. If your mass energy was only 1% of your total energy, time moves at 1% of the normal rate, and you would be moving at 99.995% of light speed, meaning you arrive at someplace 100 light years away in just over 100 years, as everyone else observes you, but you will think only a year has passed. From your perspective, the distance shrunk. From everyone else's perspective who is locally stationary, your watch just slowed down. And that's very real too. We have particles that have half-lives measured in tiny fractions of a second that get formed in collisions and can only live long enough to reach the detector a meter away because they have so much kinetic energy from the collision that time slowed and they live long enough to get to the detector, ones that normally dissolve before traveling the length of an atomic nucleus. Thus concludes our relativity lecture, and I'm sure you've heard it explained before, so I tried to explain it a bit differently than normal. But needless to say, this slowing of time makes an attractive option for space travel, as you may have to take a century to get to a star but only experience a year personally. Of course, that gets us to the big problem, which is that the tyranny of the rocket equation means that as long as you're carrying fuel to accelerate with, you have to accelerate not just that ship, but the fuel you haven't used yet, including what you need to slow down. This generally makes it nigh impossible to contemplate any spaceship rocket that will get you to more than about 3 or 4 times as fast as whatever your propellant is doing when it comes out the back. And even particles engaged in fusion only typically emit about 1% of their mass energy or less in that reaction. And something with 1% of its energy kinetic and 99% mass energy is traveling at 14% light speed. That means we've got to either circumvent the rocket equation or be using a propellant that moves a lot faster, and fortunately we can do both, so we have some options for spaceships that go so fast they save you voyage time, though you might need the wealth of an entire planet to build and fuel one. So what moves faster than a high-energy particle fresh from a fusion event? Not too much, but photons, gravitons, and neutrinos, and anything coming out of an even higher energy event than fusion will do the trick. Photon rockets, neutrino rockets, antimatter, black hole drives, and so on can release particles moving at ultra-relativistic speeds themselves. The other end of it is circumventing the rocket equation, which means not carrying your fuel with you. That's the way the Bucer-Durham scoop was meant to work. It just magnetically sucked in ionized hydrogen as it plowed through space and used those huge speeds to ram them together, create fusion events, pushing the ship even faster, and sucking in more hydrogen, rinse and repeat. It has its own issues, as we discussed in that episode last month, but it highlights the concept and also offers us a way to skip on carrying fuel with us to slow down. You use all that gas and dust in the interstellar void to create drag, and that rises strongly with your velocity, so helps us save a lot on slowing down, though also becomes our issue for maintaining speed. At ultra-relativistic speeds, you can't really think of space as empty anymore, as even if there's only 1 atom per cubic meter in space, at 99.995% of light speed, you are plowing through 30 billion of those atoms per second for every square meter of cross-section your ship has, and whacking into each of those particles with 100 times their normal mass energy, which would be representing about 4 watts per square meter of pushback at that point. There are much denser regions of space, and there's also ambient radiation hitting you that's blue shifted, but as you speed up this gets worse, and as you slow down it decreases. If you want to go fast, you not only need a ton of fuel to get there, but you also need to use some to keep up the speed. But you don't need it to slow down, and that's a big advantage, because normally whatever speed something can accelerate to by burning all its fuel is double what it can do if it carries its own slowdown fuel. If your ship could get you up to 10% of light speed and slow you down from there, it can get you up to 20% if you burn that slowdown fuel to speed up instead. This is why rogue colony ships can't try to beat everyone to colonize the galaxy first. They need to slow down, and a missile trailing them does not. And slowing down for free is possible, but it's also slow and requires some equipment. So what are the rocket options? Antimatter is option 1. We can produce it, and I suspect we will master both storage and producing it for some cost less monstrous than the 10 million to 1 ratio we do nowadays. We discussed some paths to that in our antimatter factories episode, and even if you had to pour in 100 times the energy to get 1 unit of antimatter out of it, there's a lot of cases where that would be just fine. That's basically how batteries work. Now, an antimatter rocket is incredibly simple. You release a piece of antimatter from a magnetic confinement into some regular matter, and the mutual annihilation releases photons. Usually. That's your rocket flame and works just fine with modern tech. But that's likely to be very high-end gamma in the giga-electron-volt region, a billion times more powerful than the photons we see, and more importantly, which we can reflect with a mirror. Almost all our ultra-relativistic engine designs work way better if you've figured out some way to reflect gamma radiation like we can weaker wavelengths of light. Of course, you might have figured out some way to make and store antineutrinos too. They have mass energy less than a visible photon, and thus if they annihilated and released photons, we could easily have that going on inside a mirrored chamber at the back of our ship and spitting them out the back as a tight and efficient beam. Similarly, neutrinos or antineutrinos are a very nice fuel or exhaust if you can make them work, given that they are so weakly interacting they can normally sail through a light year of lead untouched, so make for safe spaceship engines. Normally, any ultra-relativistic ship able to carry some crew and cargo would be a doomsday device releasing sea-torching levels of gamma radiation every moment. These are the big brother to the Orion drive, which literally uses a machine gun of nukes to move along. The nice thing about antimatter though is that it's not just it which annihilates, but the twin bit of normal matter it hits, which means you can carry that along but also can scoop hydrogen as you go. And you can also use antimatter to catalyze fusion, so antimatter offers a lot of propulsion scenarios, including a modified Bussard-Durham scoop, and there's nothing stopping one from reaching 90% of light speed. Its exhaust velocity is light speed, though what that actually means here is that it's got its mass energy, and if we're saying you could make a ship able to travel 4 times the exhaust velocity of its propellant, in this context that would mean a kinetic energy 4 times the mass of the ship, which is 20% of your total energy now, and that means you're going 98% of light speed, and distances seem like a fifth as far to you, or outside observers see your clocks moving at a fifth your normal speed. That means you're getting to Alpha Centauri in under a year of personal time, and also means people willing to crowd onto that ship for 40 years could reach everything within a 200 light-year radius of Earth, and that's something around 100,000 star systems we could settle, without having to resort to mini-generation arc ships or freezing people. We won't bother comparing the economics on any of this. It really doesn't mean much in post-scarcity civilizations and can only really be discussed in terms of energy usage. And if energy is your limitation, you will probably find you get 1,000,000 times the cargo to a star for the same energy by doing it at 10% of light speed instead, and just freezing everyone or cracking life extension technology. However, it's worth remembering that some colony ship arriving at a new star first is claiming all of its resources, and also now has access to all its starlight that was being wasted into deep space till then. Our sun gives off 4 times 10 to the 26 watts of light and is not exceptional as these things go, though most stars are dimmer, so if I get to some new star system 80 years sooner by using an antimatter rocket or similar, then I just gained 10 to the 36 joules of otherwise wasted energy, since I have a 80-year head start on my slow process to making that a Kardashev 2 system. On our post-scarcity calculation of someone being able to live a comfortable lifestyle on 1 trillion joules of energy a year, that represents a trillion years of living that you saved by grabbing that juice. Even if we only assumed a truly awful rate of efficiency in antimatter production and usage, 10 to the 36 joules is still an insane amount of energy, and when we contemplate intergalactic colonization, that scale rises by a factor of billions. So for colony ships it makes sense to get them there quickly, especially as the key is to get there first, less so with other traffic which we'll return to momentarily. We can imagine other hypothetical fuels, like trapped in a perfect mirrored box for instance, or some simple matter-to-energy converter, but our other option is a micro-black hole, and you can see our episode on black hole ships for how that can work, but a feedable one using Hawking radiation has no maximum speed, as it is a Bussard-Durham scoop variant, while an unfeedable one is going to parallel antimatter, though probably be a bit lower. As always with the rocket equation, your speed is determined by how much of your ship you're willing to fill with fuel, or in this case, how many black holes you want to keep in your basement. The best onboard option beyond something like this that isn't utterly banned under known physics would probably be something running on vacuum energy, see last month's episode on that, or an option like an intra-universe wormhole, where you might have one mouth of your wormhole in some proto-universe gushing out Big Bang fresh matter. Or if you were able to get around the causality violating issues, a wormhole with one mouth in your ship drive and one in the center of a star, again blowing massive amounts of fuel out that you didn't need to carry. Moving energy through a wormhole superluminally doesn't technically violate causality so long as it carries no information. One other cheat around the rocket equation is to lower your inertial mass. As best as we can tell, mass comes in 3 forms: the kind that reacts to being shoved on, inertial mass, and the active and passive gravitational mass, the parts that control how much you pull on something gravitically with your mass and how much you get pulled on. If you can suddenly make your inertial mass 1% of what it was, you're now going 10 times faster, or have 100 times the momentum, which is problematic because you're probably violating either conservation of energy or conservation of momentum by doing this, and I would bet on the latter holding stronger in a conflict, which is handy since that results in a higher speed. This is definitely pushing it on saying it is possible under known physics, but we do have some reason to believe inertial mass might be changeable, and makes for a nice ship drive too, since you're less dangerous to places you're approaching if you're carrying less kinetic energy than your speed and normal mass implies, and you can presumably flip your engine off to return to your natural speed rapidly, or even flip the inertial mass higher to slow even more. So too, if we had negative matter, as we consider using for warp drives or wormholes, you have the possibility of a gravitational dipole drive, which we discussed in more detail in our Advanced Spaceship Drive Compendium, but basically is able to fall toward any destination and accelerate the whole way. Back in the more plausible realms, and onto an option most channel regulars know, we can accelerate ships by pushing them with laser beams, or matter beams, or both, and decelerate them the same way, though they have the upside that they have big sails for catching such a beam far from a relay and can use those to slow by drag forces faster than a more needle-shaped ship. And we'll wrap up on this one because it's probably the best option, hence why I talk about it all the time. If I can keep a beam focused on a big thin sail, I can keep pushing energy into it to speed it up, or slow it down. You lose the ability to go off course, so you're more like a train than a ship, which wrecks the whole free spirit explorer option, but they can be used to get you up to speed, and then you could use the other methods we discussed for maneuvers or slowing. And while I always discuss this as a big mirror sail for normal or concentrated sunlight or visible lasers, this could be radio waves or ultraviolet or even just ionized matter, though that last is a bit tricky to keep as a coherent beam too, and you could also use big ion pods or pellets to magnetically decelerate down the throat of a ship, and they could carry more mundane cargo. You could send them a fuel supply that shoves on the ship as they grabbed it, and while it sounds incredibly dangerous, that could be antimatter that they were shoving you with, and that you grabbed and stored magnetically, or they could send bottles of it. It is also possible you could regenerate some of the energy used to speed you up while slowing you down. Maybe the bounced light could be redirected to energy collectors along the way or retrieved otherwise. You can capture ionized gas along the way and let the beamed energy accelerate those particles as a propellant too. Lots of options. For more on this approach in general, see our Interstellar Laser Highways episode, but one closing note. If you have effectively unlimited energy, by super technology, clock tech, or rampant indifference to using up resources, you can go fast like this, and might eventually have civilization issues with the sheer amount of waste heat and excess ultra-relativistic exhaust gas floating around. Nor do we have any great solution to the collision issue, though that's less of an issue in intergalactic space where you might be seriously contemplating aiming for some 99.9999% of light speed or greater. You can absolutely survive being hit by random hydrogen particles or bigger lone atoms at this speed. But any grain of dust, billions or trillions of atoms, even when barely visible to the eye, becomes worrisome and you need to detect and evade, deflect, or vaporize that thing. Trying to see a grain of sand a billion meters away is no mean feat. Trying to blow it up is no easier, and you have exactly 3 seconds to see and hit that thing. We discussed some workarounds like running a thin sail ahead of you to get itself wrecked on your behalf, which you can patch and recycle, but this, even more than the energy bill, is probably your limiting factor on speed. There will be a calculable cost and risks for any given speed, and likely rising exponentially as you accelerate, especially as you need to build heavier to lower your risk. No needle ship the size of a pencil with antimatter and nanobots in it is colonizing space for you. All that nanotech is even more sensitive to radiation than you or I are, so you still need thick front radiation shielding, and thus there's not much point on skimping on your cargo holds. Hence again why I always tend to describe colony ships as massive even when assuming they have nanotech. Thus I do tend to assume that by about 20 to 30% of light speed, you're hitting that maximum inside a galaxy, with the possibility of some sort of laser relay rail system parallel, swept clean by relays of dust particles. That might allow higher speed traffic in developed star systems, and that colonial efforts, particularly intergalactic ones, might go for the megaship with quadrillions of tons of cargo space and fuel, and armor, and pull off ultra-relativistic speeds. For the rest of us, we'll probably have to settle for a tenth of light speed, where clocks only run about 1% slower, but it is worth remembering that is still 100 times faster than any spaceship we've ever built, and would get you from here to Mars in about an hour, which is pretty darn impressive. And on that note, thanks for joining us for another Nebula exclusive. As you may or may not be aware, this episode first appeared on Nebula last year, which is why my speech impediment seems stronger. I try to release a new episode on Nebula the first of every month, and this month's episode is Orbital Farms, which is a loose companion piece to our recent look at early terraforming, building biospheres, and our upcoming series of episodes deep diving specific space habitat designs that will begin next week with the Stanford Torus. While you can build space habitats to contain farms and forests, not just homes, I tend to think you would see a lot of dedicated nature preserve habitats and even more agricultural space stations, orbital farms requiring less robust construction and accessories than a human habitat might need. People in space need to eat, so we are likely to see orbital farms emerge to help supply them. So too, we might grow food in space to save room down on planets and set it down on ships or space elevators from orbital farms to hungry planets. In this month's Nebula exclusive, we'll be examining those orbital farms. If you didn't know, Nebula, the largest creator-owned streaming service, has tons of extra content from myself and many other creators, including a new, full-length episode of SFIA like Orbital Farms that we release on the first day of every month. And every episode of this show also airs on Nebula a few days early and ad-free, no random commercials or built-in ads like this one. Using my code, IsaacArthur, you can get 40% off and join for about $3 a month, about the price of the drink or snack you've been enjoying during the episode. We also now have lifetime memberships and gift cards available to let you share Nebula with friends and family. When you sign up at my link, go.nebula.tv/IsaacArthur, and use my code, IsaacArthur, you not only get access to all the great stuff Nebula offers, like Orbital Farms, you'll also be directly supporting this show. So that's it for today, but we'll be back on Thanksgiving, Thursday, November 28th, for a look at the Stanford Torus Space Habitat. After that, we'll head into November to look at building biospheres on new planets and inside space habitats like the Stanford Torus. Then we'll look at a more near-term relativistic spaceship design, the Medusa Drive, on December 5th. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or at Patreon, or check out other ways to help at isaacarthur.net. Until next time, thanks for watching, and have a great week.